The last thing that we're going to do to wrap up section 3.1 is look at a brief application problem where we're going to go ahead and try and actually take the law of sines and apply it to a real world scenario. The one that's included here in the lecture slides is as follows. We have the course for a specific boat race starts at point A, proceeds in the direction south 52 degrees west to point B, then in the direction south 40 degrees east to point C, and finally back to A. They've given us a little bit of information, which is that point C lies 8 kilometers directly south of point A. Now we're going to go ahead and talk a little bit about this because we haven't actually discussed as much when we deal with directions in terms of compass directions, how they relate to angles. In this case, if you take a look at the diagram, it can help you out a lot here. When we say south 52 degrees west, this is saying, okay, from the straight south direction, we're going to, in this case, deflect 52 degrees in the westward direction. So that's what you see there at A. That angle of 52 degrees is 52 degrees deflected from a straight south direction. By the same token, when we say we're going to move south 40 degrees east, it's the same idea. We're deflecting 40 degrees to the east from the straight south direction. So that's what you see there measured with B. And this actually might seem like it creates a bit of a problem, because now the angle that I know for B isn't quite the angle inside of the triangle that I'm looking at measuring. Because in this case, to find the total distance of the race course, I'm supposed to measure from A to B, from B to C, and from C to A, and add up all of those lengths. So it'll be 8 kilometers plus the 2 remaining side lengths. So this might kind of seem like we're up a creek right now. We don't have enough information to work with. This is where we need to make use of some old ideas from high school geometry. In this case, we need to note here that with both of our directions, south 52 degrees west and south 40 degrees east, we're actually using the same reference line. We're using south in each case, and that is going to run parallel to itself. So in this specific case, here's what I want you to imagine. I want you to look at this as essentially that this segment from B to C is a transversal that's cutting 2 parallel lines, B to D and A to C. And one of the things that we know about transversals and parallel lines is that this angle, DBC, is going to be congruent to this angle, BCA. So in fact, if this is 40 degrees, this is also 40 degrees. You could think about it in terms of movement as well. If this is south 40 degrees east, moving in the other direction would be north 40 degrees west. Head in the northward direction, but deflect 40 degrees to the west. So what does that mean in terms of the actual work that we want to do? We'll take a look on the notepad and give ourselves a brief sketch. We have our angle A. We have C. We know that they are 8 kilometers apart. We head over to point B and then back to C. We know that this is 52 degrees here at A. And what we're saying is because B to D and A to C are parallel, B to C acts as a transversal, and opposite interior angles are congruent. So if that was 40 degrees, this is also 40 degrees. And now we see that we actually have more than enough information to solve for the 2 missing side lengths. We could go ahead and start by finding the remaining angle here. Let's go ahead and find B by taking the sum of the 2 known angles and subtracting from 180. These add up to 92. So 180 degrees minus 92 degrees will give us 88 degrees for the measure of angle B. This is important for us to know because this is going to be something that we actually use to set up one of our ratios in our proportions to solve for the remaining side lengths. In this specific case, we have, so far, we know B, which is going to be 8 kilometers, and we also know the measure of angle B now at 88. So I'm thinking of using B over sine of B and putting it with A over sine of A. This will allow me to solve for this distance right here. And if I set up a similar proportion with B sine of B equal to C over sine of C, that'll allow me to find this distance here. I'll take the sum of those lengths and add the original 8 kilometers that's also part of the course, and we'll get our total length. In this case, if we go ahead and substitute in, the expression for A is going to be 8 times the sine of 52 degrees divided by the sine of 88 degrees. This will be given in kilometers as well. C is going to look very similar, the only difference being that it'll be 8 times the sine of 40 degrees divided by the sine of 88 degrees. And again, this will have units of kilometers as well. In this case, since we're dealing with a real-world problem, we could go ahead and leave our answers in exact form, this plus 8, but it makes more sense to go ahead and, for this one instance, give ourselves some approximations to work with. In this case, the length for A is going to be approximately 6.31 kilometers. And the length for C is going to be approximately 5.15 kilometers. Double check, make sure that the sides opposite angles match up here. So the shortest angle was the smallest angle was 40 degrees with C, and the shortest side length was also C. The greatest of our angles, 88 degrees for B, also had the greatest side length opposite with 8 kilometers. The final answer here is the sum. This is going to be 6.31 plus 5.15 plus 8, or in this case, approximately 19.46 kilometers. One thing to note here about this specific application, this really didn't have that much real-world usage. This is something that, yes, is determined through the use of trigonometry, but doesn't explicitly require it. This is something that could be measured in other means. So this is more of taking a normal problem using law of sines and just putting a little bit of window dressing on it to turn it into an application problem.